you received your materials in the mail to build the models, and I think I'm going to hand it over to Claire to take us to the next part. Are you?
Okie dokie. Sally, would you mind stop sharing your screen?
Oh. Okay, how do I do this? Wait a minute. I was trying to figure out what, okay.
So go up to the top, and you should get that pop-down menu, and it should just be able to
stop share. Oh, there it is. Okay.
Yeah,
and now I feel good. Okay.
And then,
sorry, guys.
No problem. And then for the rest of, I'm sorry, Sally, go ahead. What?
One more comment. I think if you try just saying, you know, if you're teaching high school and you just have a use for something like this because of what you've seen, just say, you know, in your whatever class or earth science or geology or art or whatever, that this would be very useful. I think they'd be very open to that.
Wonderful. That's so great.
Okay,
that's a really good point.
Honesty.
Wonderful. Thank you. For this next little bit, if everybody can make sure that their view is in the speaker mode, so not the Brady Bunches, but where you get the strip at the top and the big blocks, because what we're going to do is while Claire's showing us how to use the model, or how to put together our models. Ricky, did you start the meeting? Are you the one that is able to know you didn't? Okay, I would say whoever started the meeting is able to lock us into the host piece so that everybody can talk and ask questions, but it won't leave Claire's screen, and we'll just continue to see what she's seeing. So if you can put your mode that way, otherwise it'll just be, you'll just get the green box around Claire the whole time. But take it away, Claire.
Okay, so Ricky, are you the host?
I am.
And so can you click on my picture and just click spotlight? And that way it will stay focused on me. And it means everybody else can have a discussion, but that will just stay, we'll stay focused on the model that I'm about to build.
Okay.
Okay, so good. That's perfect. Okay, so that means that you can have a discussion and we won't have to worry about it switching and changing for a few minutes. Okie dokie. So in the mail, you should have gotten some materials from Andy. And what I'm going to do is take you through the early stages of putting the bases of the model together. And once we have the model built, then I'm going to pass it on to some of our MAVEN Educator ambassadors, and they're actually going to walk you through the process of doing the activity. So I'm just going to help to build the model in the first place. So hopefully all of you have the full screen of my webcam, so as you'll be able to see in detail what it is. So let me do this. This is very this is always very weird where you have like the full screen right here rather than it being the Brady Bunch mode. That looked really trippy, so don't worry if it doesn't look exactly like that. Okay, all right, so the first thing that we're going to do is, first of all, does anybody have any questions about materials or anything like that before we get started, or will we dive right in?
Can you give a PSA about the magnets, Claire? Before?
That's what I'm about to do. Okay, so the magnets that you will have received are extremely strong. So whatever you do not let them touch off each other, because if they touch off each other, you're going to have to get a pliers to get them apart. I keep mine on either side of a post-it note pad, because even if I just use a piece of paper, the paper will just rip apart. So be very careful as we're going along not to let these touch off each other, or you'll have quite the job trying to get them apart. Also, keep them well away from any electronics. So if you have your cell phone on the table, you might want to consider just moving that away, or make sure you don't place the magnets on your computer or too near your computer, or you might damage your hard drive. So just be very careful with these, okay? In particular, these really strong neodymium magnets. Okay, so to begin with, you can have a piece of cardboard or a chopping board, or you can just do it directly onto the tabletop if you wish. You don't have to have something. By doing it on this, it just means that you can move it around afterwards. I'm going to move.
Oh, Claire, something you didn't know is that I included a piece of masonite in the boxes that we had at the planetarium from a different kit I had. So they also have a white piece of masonite.
Okay, perfect. So that's going to be your basis. So let me just move this. Okay, so everybody can see my tabletop clearly enough? Okay, so we're going to start with one of our magnets. And again, be very careful at this point because they still like to touch each other. So I'm going to take this other magnet that's hiding under here and I'm going to place it well out of my way. So I'm just going to take one of these and place it on my cutting surface. Now at this point, I would recommend that you break off 6 or 7 strips about 2 or 3 inches in length. You're going to need quite a lot of tape because these magnets are going to want to stick to each other. So break off a good few pieces of your tape. If you only have sticky tape, that may not work because of the strength of the magnets. So at this point, I think everybody should be working along with me. So this is a make and do kind of a special. I feel like I'm in Blue Peter, which of course is something that you don't get over here. Okay, so I have my pieces of tape, and I'm going to start by just sticking down my first magnet really well. All right, so make sure that the tape is nice and tight, in like this. And this is all detailed in the teacher guide of the magnetism activity. Okay, I'm going to put 3 pieces of tape down here.
Claire, this is Nancy.
Hi, Nancy.
Do you want me to take notes on this?
No, I don't think so.
No? Okay.
I think we're okay because this is all just detail. If there's interesting discussion or questions or suggestions that come out of this, those notes would be helpful.
Sounds good.
Okay, so we have our magnet well and truly secured to our tabletop. Is everybody with me so far? Okay, all right, the next thing that we're going to do is we're going to take our cow magnet and we're just going to figure out what polarity this magnet is. So this piece is important. This is like a calibration. So I'm just going to touch the cow magnet off of the first circular magnet just to get an idea of the polarity. So this is sometimes easier if you use a magnet with a blue and a red end, because then you can remember which way is up or which way is positive. I'm just going to try and remember, so I'm going to gather all of the leftover iron filings onto the top of the magnet right here. So this is the end that I'm using just to remind me which way it is. So this is attracted to my magnet down here. So this is going to be important in just a minute, because I'm going to take my second magnet. Okay, I have it in my hand right here, and I'm going to touch the same end. So just make sure, yeah, that's still attracting. And I'm going to figure out what the opposite polarity is of this magnet. So I want it to be repelled. So that's this way up. So this is being repelled. This way is attracted. Okay, be careful you don't pinch your fingers. And this side is being repelled. So I want the opposite polarity to be up. Now this is quite tricky. Okay, so at this stage, if you have your golf pencil, you can place your golf pencil right in here, right in between where these 2 magnets are going to go. I don't have a golf pencil. You don't need it. It just makes life a little bit easier. So what you do is you very, very carefully place your magnet down. You've got to keep a good hold of it, or it will just flip itself over and stick itself to its next door neighbor. So keeping a good grip on the magnet, I'm going to sellotape it down as well. Okay, so again, 2 or 3 pieces of tape to make sure that it's well and truly stuck. It doesn't matter if the tape overlaps with the other piece right here. Okay, so now we have 2 magnets that are well and truly stuck to the table, and just as a final check, I want to make sure that they are in fact opposite polarities facing up. So this is being repelled and this one here is being attracted. So we're in good shape. Okay, so I'm going to give everybody just a minute or 2 just to make sure everybody's caught up. And in the meantime, for those of you who are quick study, at this point, you could, if you wished, color the 2 magnets different colors. You could color one red and one blue. So for your students, that it's an indicator that they're different polarities, but it's not essential. That would just be an added bonus. Okay.
That would be really helpful for your visual learners, or those with short-term memory issues. That would be really helpful for them, I'm guessing.
So when we did this in July, when we were in Colorado,
yep,
this is already done for us. So
because this is kind of a pain to do, insofar as we had no idea to try it. We had, I think, 10 different kits. So to try and do this process with a big roll of these very strong magnets, just the way it had, but we had them all built from a previous experiment.
Right.
I would recommend, especially for younger students, that you go through this process. You just get them as far as here, rather than giving the responsibility to your students, because of the possibility of pinching. because these magnets are so strong. We did a lot of experiments with this to try and figure out what magnets we could use for these. And we tried multiple stacks of weaker magnets. We tried larger and weaker strength. We tried smaller size, stronger strength. And these worked out to be the optimum ones. Anything weaker doesn't have enough of an effect high above where the magnets are. So this is why they have to be as strong as they are, okay? So obviously it's your call. If you think your students can handle this, then great, but just be aware that the likelihood of pinching is pretty high with these. So is there anybody still working on this, or can we move forward? Everybody ready to move on? Yeah? I can only see 2 people nodding because of the way that the setup is. So I'm going to trust that if you're still working, that you'll unmute yourself and you'll let me know. Okay, so next of all, we have the teacher guide, which is available on the website. Actually, maybe at this point, I will just pause for a moment, and I'm going to share with you where to find these resources.
I did put copies in the box as well, Claire.
Okay. I think it's still useful.
Oh yeah, no, absolutely. Just for your information. Okay.
So I think let's just share desktop. So if I pull open this and I go to, so if I just search for MAVEN LASP, then the MAVEN Laboratory for Atmospheric and Space Science, Space Physics website comes up. So this is the main MAVEN mission page. Okay, can everybody see this? You can see the countdown to the Mars orbit insertion here. So up on the top row, we have education and outreach. And under education and outreach on the left-hand side, we have for educators. And under for educators, we have MAVEN Educator Ambassador Project. So if I click on MAVEN Educator Ambassador Project, then it brings me to the main MEA homepage. And this last lesson here, Planetary Magnetism, is the lesson that we're working on. So we have the teacher packet and the student handout. And we're working on the teacher packet right now. So this is what we have right here. And so we have just gone through this initial stage of building. So you can see where the golf pencil is right here. It just helps the 2 magnets to stay apart. We actually realized that that's not really essential. It's just maybe an added bonus. So we're going to move on to the next phase just now, which is just putting the basic apparatus together, okay? So if we go back here, then the first stage of our apparatus building is to take our 2 of our 4 spacers. So we've used DVD boxes because they're about the right size and they are easy to come by. So all of this whole activity was designed with ease of access in mind. So aside from these strong magnets, the hope would be that much of the rest of the equipment would be readily available, or at least easy enough to obtain. So we use 2 DVD boxes, but you can use anything at all that's roughly this size, provided of course it's not metallic or it's not magnetic to get attracted to the magnet. So we're just going to place 2 DVD boxes either side of our magnets. And I'm just going to very quickly cut to the schematic, which is very handy. So we're looking at this schematic right here, which is at the pages are not numbered. This schematic right here in the teacher guide. So on top of our DVD cases, we're going to place the surface of Mars. So this is the surface of Mars. So beneath here, the magnets, where the magnets are, is beneath the surface. So that's our crustal magnetic field. Okay. So we have our Mars surface here, and then on top of this, we're going to place the regular atmosphere by just using one of our thick acrylic sheets. So this is just the standard lower atmosphere of Mars. Okay. On top of this, we're going to have the next layer of Mars's atmosphere, and we've used lamination sheets, but really just anything that's somewhat pliable, but also quite sturdy and preferably transparent would do. Okay, so, and these lie on top of each other. So is everybody with me so far? Yeah, anybody have any questions or problems? Okay, so at this stage, I think I'm ready to hand over to the MEA teachers who have already done this and have agreed to lead the actual activity. And I think at this point, you might want to pull out your student guide of this activity, and we're going to work through the student guide. So is there MEA who's going to take over from me from here? Lynn, Sally, anybody? There's somebody speaking, and oh, you know what, Ricky, you have to unspotlight me. I can cancel the spotlight. There we go.
There we go. Yeah. Yeah, Lynn is gonna set. She has her stuff set up to be able to do, and then Sally and Molly were gonna co-op to take us through the activity.
Okay, Lynn, are you there?
I am. Can you hear me?
No, we can't see you though. Your video cameras are turned off.
That's because I've got 2 cameras.
Well, I see your face, but I don't see your table.
Hang on.
And then we can get Ricky to spotlight the table camera.
Can he see that? Oh, there it goes.
No, not yet.
Yeah, it's first. So we did practice. It was so good. Yeah, it was.
Yes, we did.
You're there. Okay, we see a strip, Lynn. It has movie controls on it.
It went to sleep.
You know what will happen here? Okay, it went to sleep. Also, if you mute that particular camera and then turn the one, like I'm looking at Lynn too, and yep, there we go. We can see your face. That might help until you get the other camera up. I don't know. I'm just thinking, maybe not. Because when you speak, we see your camera with just your avatar. There it goes. Now we got it. Okay. Ricky, can you spotlight that screen for us? All right. Go ahead, Sally and Molly.
Well, I noticed that Lynn has put her whole model on a cookie sheet. So, Lynn, why did you do that?
Because it helps collect the mess.
Then can you pull it back towards you just a tiny bit? It's up a little bit close to the camera.
There we go. Okay. Because iron filings are really a pain. And we didn't use baggies at all.
They were. You didn't have to take responsibility for cleaning the cow magnets afterwards.
I know, but I had a question on it, and I think I was the only one who really did, because I was concerned with when you had kids, middle schoolers especially, or it's just getting how to get them off and how to make sure they're not in your face. We touch our face so many times, and I guess I'm very conscious of eyes and things like that. So would you recommend goggles?
You could do, certainly. I'd imagine that's probably a good idea, especially with younger students.
So
I teach 3rd through 5th grades, and I would strongly recommend wearing safety goggles, just because, Sally, as you mentioned, it gets in your hand, kids tend to kind of rub their face or whatever, and then you don't want them to inhale it and put them in the mouth. So I would just, safety goggles would be good, just for the younger kids. So, and Sally, Lynn, were you gonna show the little plastic bag?
yes,
Yeah. Okay. Mm-hmm.
right there. Putting the cow magnet in the plastic bag helps alleviate some of that mess.
Yeah.
So, which is not in the instructions, but just from our experience. So.
Okay.
So Linda's going to she's putting the iron filings on, and it's interesting because this is a model. We're creating a model, And we're really creating a model of, which I only did this once, and I had the whole kind of a different take on it, of the iron filings, or the cow magnet is like the solar wind, so it gathers up all the particles of the atmosphere, and you can just maneuver it. So just try working, seeing what happens. But having not done this only but once, and then not thinking about it and not reading the directions, I took this model in a different way and thought it represented part of the magnetic field that Mars has in the southern atmosphere, and not a global field like Earth has. But so that wasn't the intent of the model at all. So anyway, so Lynn, what are you doing with the? That looks like doesn't that look great? What an art piece.
Mm-hmm. Shall we have a solar storm?
Yeah, let's have a storm.
Remember if you're going to have your solar storm, we got to go to the next level.
Well, okay, should we just have solar movement now?
Are we ready to move on?
We are ready to go. So what do the iron filings do as the solar storm comes near?
Well, hang on, because let me just remind you to put the next level of acrylic where you start bringing your
Oh, there's another sheet. Okay.
There's another sheet. So you would put the other acrylic on top of that.
And then
but before you put it on top, make sure you have another set of DVD players.
Oh, yes.
You have to put the DVD players.
Hang on.
We've lost your webcam, Lynn.
I know.
So if you place the two DVD boxes, the next two spacers, whatever your spacers are, on top of the original two spacers, and place the second piece of acrylic on the top of those second level of spacers.
Mm-hmm. Is this the activity, Claire, that was backwards?
It was backwards.
It up backwards.
There you go.
We had them wrote out on the desks previously, and then we had to
Right. Okay, because I remember.
zoom out a tiny bit now. There you go. So see the second set of spacers and the second acrylic sheet on top of the original acrylic sheet. So be careful that your spacers are not too big, because they won't interact with the magnets on the bottom sheet as strongly. So the bigger the space between the acrylic sheets, the less impact it will have. Distance makes a difference. So it will be okay, but single DVD boxes are kind of the size.
So Lynn, we can't, oh, there we go. Okay, we can see the.
Okay. Everybody with us?
Yep.
So we saw a lot of movement, and then we.
Can you see it?
Yeah, I can see it.
See, I've got some of it moving off when the solar wind comes through.
So everybody can be doing the same. If you take your cow magnet, actually using a small amount of iron filings is a good idea. Too many iron filings gets difficult to deal with. And the idea is that you're just going to try and manipulate the iron filings around and see what happens, and just observe the interplay between the place with magnets and the place with no magnets, and what happens in the different scenarios. So what are you starting to do?
What do the magnets at the bottom represent in this model?
So the magnets at the bottom represent the crustal fields of Mars's atmosphere. You guys want to unmute your microphones, and we can have a discussion about what we're seeing here. What are you starting to notice just from playing around with the iron filings? And you can take it apart and redistribute the iron filings if you need to, if they start to get too stuck.
Okay, so this is a model of what happens with the particles in the atmosphere from the solar wind, right?
Yeah. So
then, so those other magnets are below the surface of Mars.
mm-hmm.
Okay.
So what we see here is this is modeling is that the iron filings that we have sprinkled here are supposed to be ions in Mars's atmosphere.
Okay.
And the cap that we have here is supposed to represent the solar wind or a coronal mass ejection. And so the magnetic field coming from the solar wind is going to interact with the particles that are in Mars's atmosphere. But what we want to observe is what happens to the particles that are in Mars's atmosphere close to the crustal fields versus what happens in the atmosphere where there's no crustal field. So remember that the original circular magnets are the crustal fields. So Linda, I'd like to recommend that you get rid of some of the iron filings. I think you might have too many there. That might help a little bit. So if it gets to the stage where all your iron filings are piled up on top of it, then you can take off the top layer and take off the top of the DVD, and you can lift off the translucent page and just shake them out again, just redistribute them and put them back into the box and put them back out again if you have to. And then we're going to put the
Uh-oh.
What happened?
You knocked us over, Lynn. Just threw us on the ground.
Oh, no.
Maggie, Mars doesn't have a magnetosphere like we think of it. They do have magnetism, and they do have small holes in the southern hemisphere, but it's not like Earth.
I have a question.
Yeah, question.
The iron filings represent particles in the atmosphere.
Mm-hmm.
What particles are those?
They're ions. So we're actually going to go into some of the science in a little while.
Oh, okay. Sorry.
And then we'll go into the detail in a few minutes. So want to go on to the next piece, the bit with the coronal mass ejection and what we're aiming to do. So the first piece was just exploring and seeing what happened. What's the next stage of the activity?
What's the next stage?
So the next stage is we're actually going to try and take off Mars's atmosphere. So we're going to, this is where the baggie comes into it. We're going to move the cow magnet across the top of the surface of the sheet. And we're going to try and avoid the crustal fields and try and actually remove the atmosphere. So this is where you want your cow magnet to come away with actual iron filings stuck to it, okay? So this is why you might want to and as you do this, then you might want to have just a little jar or something to put your iron filings back into, or a little plastic cup or something like that for your students. You should only be giving your students about a tablespoon of iron filings anyway. And then they go back to the jar. And the idea is trying to basically remove as much of Mars's atmosphere as you can. And the exploration here is the discovery of what happens when you're interfering with Mars's crustal fields versus when you can, if you have to pass directly over the crustal field, does that trap some of the iron filings, or in this case the Mars's ionospheric particles, or does it let them go? So this is a kind of an interplay between the forces of gravity and the force of magnetism between these two in Mars's atmosphere.
Claire, what do you mean by crustal fields? Maggie's wondering. I don't know you're
crustal fields
a little bit.
Yeah, the crustal fields are represented by the two circular magnets that we stuck to the board at the beginning, and they are They are magnetic fields that come out of Mars' atmosphere. They look a little bit like beehives, and that's all we have of the magnetic field of Mars. There's no global magnetic field like we do on Earth. We just have these little bubbles of magnetic fields. They're little small beehives. And so what we're trying to do is look at the interplay between the loss of Mars's atmosphere and where the magnetic field on Mars is. Does that make sense, Maggie? It'll make more sense soon, hopefully. Yeah.
Here's my question.
Wow.
Now, let's assume you do have a magnetic field that's holding your ions in place, but as the magnet gets strong enough, it's also going to start stripping it off, will it not?
Say that one more time. Vic, can you repeat that one more time?
I was going to say, even if you'd have a very strong magnetic field such as the Earth, when you run that coronal mass ejection over the top of it, it would still strip the topmost portion of the atmosphere, would it not?
Well, that's a good point, because if we pause for a minute and think about our setup right here, and whether or not we're thinking about just the Mars's crustal fields or the Earth's magnetic field, what are the forces at play that are keeping these ionospheric particles or iron filings on the surface or in the atmosphere of Mars? What's battling our cow magnet coronal mass ejection? There's two main forces that are battling our coronal mass ejection. What are they? So there's the force of gravity. So there's
gravity and then the attraction of the magnetic field.
Magnetic field. So the strength of the coronal mass ejection, if you had no surface magnetic field, the solar wind would everything. Okay, it would strip all of the charged particles away. But because we do have some amount of magnetic field on it, that does have a real strength to it, even though it's localized, they are still pretty strong fields. The strong only have a certain amount of effect. It still can't take everything away. So if we go through the action, if you redistribute your ion filings and you just the cow magnet across the area with the crustal, you may notice that at the beginning, lots of iron filings that it picks up, but as soon as you pass over those crustal fields, it pulls them all back again, so you lose them. You can't just take them away without cost. It's also interesting to flip your bar over, try and go the direction and see if there's any change in how much of the magnetic field that you can gather up. So this is really about exploration. It's about wondering the balances between the magnetic strength of the crustal fields, the magnetic strength of the coronal mass ejection, and gravity, and how those three forces balance each other out. And they're not the same all over the planet, and they're not the same on every planet. So in this activity, there's a further section that questions these kind of effects on Venus as well, and on Mercury too, I think. Okay, so this is really just an exploration activity, and you can have a lot of fun with this. You can basically, we try and make it almost like a game where the aim is to try and steal as many iron filings, try and strip away as much of Mars's atmosphere as you possibly can in a single stroke or in two strokes. And what happens if you don't go anywhere near the crustal field, or lots of different variety on the thing. And all the while, the idea is to have a discussion, to be asking questions about what it is that you're seeing, what are the interactions. And when I do this with students, I like to not tell them that there's magnetic field, there's magnets stuck to the cardboard. I like them to try and figure it out for themselves. So that's always the first way, trying to figure out what's going on, what are we seeing here. So that's all part of it. So. Anybody else have anything they want to point out, or what else are you noticing about what we see here? What if you only use a single end magnet?
Claire, in your PowerPoint later on, do you have that diagram that shows the magnetic fields in Mars' southern hemisphere?
Yes, I do. So I'll get to that in just.
I think that would clear up some of the questions that are coming up on the chat.
Can I make a little comment in regards to the setup? I've noticed in the way we set it up tonight was having the magnets on the top, but I've noticed that if I have it on the bottom and the cardboard is on top, that I could easily slide my coil magnets easier and pick up more filings and slide it across than if the magnets were on top. So I don't know if anybody else experienced that, but
a good point. And why do you think that is? What difference is that bit is being made with having the piece of
coil magnets being on top? It's going to make it a little bit stronger, and so it'll pull the filings a little bit. There's going to be two forces that are going to be competing against each other. And if if the magnets were on top, it's just a stronger force than if it was on the bottom of the cardboard. The cardboard might, not have the same strength. Yeah, that's what I would think.
Yeah, so that's a good point. So if you wanted to dismantle your setup, you can turn your cardboard over and then put it back together again. So your DVD boxes, and then your paper and acrylic sheet, and then laminate paper, 2 more DVD boxes, and then your acrylic again. And you do the same interaction, and you can look to see if there's any change in how much of the iron filings you can put away. And I've just done it there, and it's actually quite remarkable. I can almost get the entire bundle of iron filings off of this. So that's actually the purpose a little bit. We do want the crustal fields to remove some of the iron filings, or that whatever your setup is, and that will depend on the thickness of your cardboard and the size of the boxes and the thickness of acrylic and a whole load of other stuff. But you want to make sure that you're not actually losing all of your iron filings. You do want to keep some of them behind, because then you can have a discussion about how them are being by others. So Chris, do you have anything to add from last year? You have a different year's perspective on all of this. Have you tried this in the classroom yet, maybe?
I will be when I have students. And I'm glad I did this again, because I find it interesting.
It's fun. It's a good kind of entertainment / educational activity, because everybody loves a good iron filing. So if we look at this is in the student guide. So if you go to the student guide in the bottom of page 2, you can actually see this schematic picture that shows you what it is that we're trying to represent with our model, right?
There was a big difference between Lynn's cow magnet picking up files compared to yours, Claire, and you aren't using the baggie. So that plastic, that's interesting.
Well, no, right now I have, I followed Molly's suggestion, and I turned over my cardboard and it took everything away. So if I undo what I just did, so right now my cardboard is hiding my magnets, which are on this side.
Okay. But I meant the bag. I meant putting the,
if I go back
in the baggie.
I don't know if that will make much of a difference, because when I had the setup this way originally, I was able to pull far fewer off. So if I do that again, you can see that most of them are actually retained. Most of them.
Right, but okay, because Lynn put the cow magnet in the baggie, and she was
barely have too much. Yeah, I think the spacers is probably more.
Okay.
So I would imagine that maybe Lynn's spacers are too big. So if your spacers were a little bit smaller, then you might have more success.
So Maggie she had a question in the chat box about comparing this to Earth's atmosphere, how you could use this to do that.
That's a good question. We don't have an activity specifically for that, but there is a discussion on this in the presentation that we're going to do in just. So maybe after that we could have a discussion on some ideas that you might have on how we could compare it to Earth's atmosphere.
Fabulous. And Chris, did you want to share what some of your experiences have been? I saw that you tried to I know you had to jump through hoops to unmute.
Well, I just unmuted myself again. You guys hear me?
Yeah.
Yeah? Okay. I've used it with my students a few times, and definitely the plastic bag would be a great addition. It's always a lot of fun to try to strip all those iron filings off of your comm magnets to use them again later. Also with teacher workshops, similar types of things. I use smaller sheets of plastic. I got like photo frame replacement plastic pieces that are 8 by 10 from Lowe's, just to save on money to put together kits for my workshops. They seem to work okay.
Good idea.
So one of the final questions, or one of the questions on page 4 of the student handout is, based on your observations, does a planet's magnetic field help to protect its atmosphere from being stripped away by the sun, yes or no? So there's a whole series of questions here that will hopefully help guide your students through the exploration and help them to put 2 and 2 together in what we're seeing. And then there is a going further section that starts on page 6, and then going even further, which involves some math as well for the older students.
Mm-hmm.
So does anybody have any more questions, or maybe we should do the science background first, and then we can have a discussion and talk about some questions after that. Would that be helpful?
Yes, that would be good.
Are you also going to show the sputtering video?
Yay, that's a good one.
Which video?
Sputtering.
And Claire, there's a comment in the chat from Vic about, so MAVEN, according to this model, will find higher concentration of ions over the magnetic field and lower in other regions.
That would be a hope. I'm not exactly well, yes, I guess they are doing those deep flight or the deep orbit analyses. So I would expect that that would be the case, that's what they're hoping to see. So there's a number of different loss mechanisms for stripping of Mars's atmosphere, and MAVEN is trying to investigate most of them. I think at least 3 of them. So how do you tie the ions to the actual lower? I don't quite understand what you mean by that.
The ionosphere is above your normal atmosphere. How do you tie that? That's also what the atmosphere itself has been stripped off. How do you tie the 2 together? Because with the ionosphere, you can deal with a charge and magnetic field. The atmosphere isn't. So how do you make the correlation between the 2?
So let me just see if I can repeat your question, because you sort of cut out a little bit. So are you saying that in the ionosphere you expect to see charged particles, but in the atmosphere you don't expect to see charged particles? So how do you connect the 2? Is that what you were asking? Yes. So that's true in the case of the Earth, because the ionosphere is a significant layer of the atmosphere, but that's not necessarily the case on Mars. So when I play the 3 videos at the end of the science presentation, that might help clear that up a little bit. And if it doesn't, then we can come back to the question. Okay? All right, let me just go to this because I'm aware that we're kind of running out of time. So this presentation is also on the MAVEN website that you can share with your students or just use as background information for yourself. Okay, so planetary magnetism. There we go. So the solar wind is a stream of mostly charged particles that emanate from the sun and blow throughout the solar system, and the sun's magnetic field flows within these particles. This cow magnet that we used earlier is supposed to emanate the sun the solar wind or specifically a coronal mass ejection. The difference between those is not super important right now. So this is the picture that I think would have helped Maggie out. This is the picture of Mars's magnetic field. Mars's crust has small pockets of magnetic fields, and the atmosphere is covered in these pockets, but only in the southern hemisphere. So you can see that in the northern hemisphere, there's almost no magnetic field. And why that's the case is an open topic of conversation. People don't really understand. There's some hypotheses, and MAVEN is hoping to help understand why this deviation is like this, where they came from. And scientists think that a lot of this come from Mars's evolutionary history, so how Mars actually evolved as a planet and how it got to be in the state that it's in. So in this case here, if you look at the schematic at the bottom of this picture, you can see the brownie color at the bottom is Mars's surface, and you can see the magnetic field. Let me see if I can zoom in on this a little bit. Oh, too far.
There, okay.
So we have Mars's surface. Oh, there we go. Mars's surface is brown, and then you can see the crustal magnetic fields are these orangey fields, and they're rooted in the surface of Mars. So they emanate from beneath the surface of Mars. So we have the surface and underlying crustal magnetic fields are orange. Above that, we have lower, more dense neutral particles, which is the bottom layer of acrylic that we have on the right-hand side. Then above that, we have the ionosphere, which contains the charged particles that Vic was asking about a little while ago, which is in our model here, it's the space between the two acrylic sheets, really. And then we have space and the sun's magnetic field, which is kind of everything above the second acrylic sheet. All right, so that's the setup of what it was that we were looking at. So why do we care about the magnetic field? What's such a big deal about the magnetic field? So magnetic fields are important for protecting the atmosphere and keep it from being lost to space. And an atmosphere is necessary for the presence of surface water, which is necessary to support life as we know it. So we have and in order to understand life, we need to understand water. And in order to understand water, we have to understand the magnetic field in the atmosphere. So NASA has a phrase called follow the water. And this is a large part of its push to go to Mars, is where did the water go? And we have seen evidence of liquid water on Mars, on ancient Mars, through some of the rovers and the orbital missions that have been there. And this started how many centuries ago with just observing the canals on Mars, and of course they're not actually canals, but this was the start of the hypothesis of liquid water on Mars. So water on ancient Mars means that there must have been a higher surface pressure. So we know that there's a pretty strong evidence that there was once liquid water flowing on the surface of Mars. And in order for that to have been the case, there had to have been higher surface pressure. And number two here, if the surface pressure was higher, that implies there had to have been atmosphere. And in order to retain an atmosphere, the best way to do that is to have a global magnetic field like we do on the Earth. So this is the kind of reverse thought process of how you can compare Mars and the Earth. And so ancient Mars may have looked a lot like today's Earth. So in these two pictures, you can see that they're quite similar. The chances are that way back when Mars had a liquid core, that it would have had a global magnetic field, not unlike the Earth's today, that would have helped to keep the atmosphere protected. Now, a magnetic field is not the only thing that will help to protect your atmosphere, but it definitely plays a pretty strong role. So today, the Earth has a global magnetic field, like a bar magnet. It has surface water, supports life, and has a thick atmosphere. And so based on our reverse thought process on the previous slide, does that mean Mars once had these things also? And then going forward, does that mean that the Earth is destined to follow the path that Mars is now following? So this is why we have MAVEN, because we don't know the answers to these questions. These are all still hypotheses and open-ended questions. So they're hoping that MAVEN will help to address some of these. So this is why do we care about the magnetic field and its interaction with the atmosphere? Well, a global magnetic field helps to protect a planet's atmosphere from harmful effects from the sun, magnetic field, and space weather. And so you can see these are two different images on the right-hand side here of the Earth's magnetic field. So you can see in this, Earth is this tiny little dot in the middle, and then we have this big teardrop-shaped magnetic field that most of you are familiar with, compared to Mars, which has barely little pimples on its surface of magnetic field. And so its atmosphere can just get blown away without any difficulty whatsoever. And the Earth's magnetic field is not only vital for life, but of course, as we all know, and hopefully some of you witnessed last week, it's also part of the generation, an integral part of generating the aurora at our poles. And so this is just one of the nice byproducts of this. So there has been an investigation started because of this, because of the small crustal fields on Mars. People are now wondering, does that mean that we should see teeny tiny little aurora spotted all over the southern hemisphere of Mars based on where the magnetic field bubbles are? So who knows? And we know that all of Earth is protected by a very strong global magnetic field that Mars does not have. So if we compare the size of Mars in here to the global magnetic field that it has, compared to that earlier picture of Mars with its little pimply magnetic fields. And I'm not going to go into this just now, the generation of Earth's magnetic field, since it's somewhat different to Mars. So today, Mars has no liquid water on its surface and no global magnetic field. And if we compare the two sizes of the planets, we can see that Earth is quite a bit bigger than Mars down here, but in comparison, the size of Earth's magnetic field compared to the size of Mars's magnetic field, they're not to scale. It's not like Earth's magnetic field is the same size relative to, it's not like the magnetic field of Mars is the same relative size just because Mars is smaller. They're really quite different. And we know that the atmosphere of Mars today is less than 1% of the thickness of Earth's. So what happened to Mars? So it's all of these things don't add up. It's not a linear process. It's not based on size. And this is what MAVEN is hoping to answer. So this is the purpose of MAVEN, is to answer these big questions. So I love this picture here because it actually shows the thicknesses of the atmospheres relative, well, they're not to scale obviously, but that Earth has this nice big thick atmosphere in the background and Mars is a much thinner layer. And MAVEN will orbit Mars to explore how the sun may have stripped Mars of most of its atmosphere, turning a planet once possibly habitable into microbial life into a cold and barren desert world. Its 9 instruments will observe Mars's magnetic field, its atmosphere, and the effect of the sun on the planet. So this is a little bit more detail about MAVEN. It has 9 instruments, which I won't go through just now because I'm aware of the fact that we're running out of time. These are some of the, these are just the groups of instruments. So we have solar instruments, we have plasma instruments, and neutral instruments. And these are really what I want to play you here. So these are the 3 YouTube videos that have been put together by NASA that describe the 3 loss mechanisms for MAVEN. So, oh. This is not going to share. Can everybody see the YouTube video?
Mm-hmm.
Yeah, Claire, we can see. There we go. Perfect. Thank you.
It appears to be a barren, dusty world with only a very thin atmosphere. However, some scientists think that Mars may have once had a much thicker atmosphere, maybe even one more like ours on Earth. So how does a planet lose so much of its atmosphere? NASA's MAVEN spacecraft will help give us clearer answers when it studies Mars's upper atmosphere, but scientists think that several processes may have had an impact over billions of years. One way that an atmosphere can be lost to space is through a series of what are called neutral processes, which are processes that involve neutral particles rather than charged particles. On Mars, for example, atoms and molecules of hydrogen gas can be found in the upper atmosphere, and they often collide with each other as they make their way around. For the most part, the molecules are still bound to the planet by. However, if a fast-moving molecule collides with another molecule at the right angle, the molecule may have just enough speed to leave the atmosphere and be lost to space. As this process continues over billions of years, it, along with many other processes, can contribute to the disappearance of a planet's atmosphere. And since the hydrogen in the atmosphere ultimately comes from water in the lower atmosphere, it may also contribute to the loss of water over time. In the end, this cumulative effect could have transformed Mars from a bluer, cloudier planet into the red one we see today, and MAVEN will study this process and tell us how it really works.
So that's one loss mechanism, and this is the plasma loss mechanism.
Even though it's not obvious just by looking at it, scientists think that Mars, a dry, dusty planet, may have once looked a lot more like Earth, with a blue atmosphere, thick clouds, and possibly even water. Scientists also think that Mars lost atmosphere over the course of billions of years, gradually transforming into the red planet we know today. NASA's MAVEN spacecraft will help provide clearer answers regarding Mars's climate history, and scientists think several processes have had an effect. For example, there are a series of what are known as plasma processes that can slowly strip away a planet's atmosphere. These processes are started by the sun, which emits light in the form of high-energy photons. When a photon at an extreme ultraviolet wavelength enters a planet's atmosphere, it can run into a molecule that makes up the atmosphere's gases. The molecule absorbs the photon, and the energy from this impact can kick off an electron, leaving behind an ion. This stray electron will eventually recombine with another ion, and the energy the electron gives to this reaction is sometimes enough to split the molecule into its component parts, give those parts a lot of speed, and launch them out into space. And although this process occurs continuously in most atmospheres, with the self-maintaining cloud of ions and electrons forming a planetary ionosphere, the escape of atoms over billions of years can contribute to the overall loss of a planet's atmosphere. This could even turn a blue, water-covered planet into a planet just like Mars, and maybe will help us figure out exactly what happened.
So you can see that a lot of these are saying they may contribute, or they will. There's no one of these that is the be-all and end-all. All of these add together to make the loss of Mars's atmosphere a concern. And this is the one that we modeled today. This is sputtering.
When you take a look at Mars, you probably wouldn't think that it looks like a very nice place to live. It's dry, it's dusty, and there's practically no atmosphere. But some scientists think that Mars may have once looked like a much nicer place to live, with a thicker atmosphere, cloudy skies, and possibly even liquid water flowing over the surface. So how do you go from something like this to something like this? NASA's MAVEN spacecraft will give us a clearer idea of how Mars lost its atmosphere, and scientists think that several processes have had an impact. One of these processes is called sputtering, where atoms are knocked away from the atmosphere due to impacts from energetic particles. In our solar system, the sun constantly emits high-energy photons. When one of these photons enters the atmosphere of a planet, it can crash into a molecule, knocking loose an electron and turning it into an ion. Ions by themselves don't do much, but when a magnetic field is nearby, they'll spin around the field. Conveniently, the sun generates a giant magnetic field that is carried by the solar wind. As the magnetic field sweeps past the planet, some ions will get carried away. Other ions, depending on where they form, won't get carried away, but will hit the top of the atmosphere. These ions can then crash into other molecules and fling atoms everywhere, like a cue ball in a game of pool. Some of these atoms can be knocked, or sputtered, into space, causing atmospheric loss. And over billions of years, this could have caused quite a bit of change, especially since solar wind may have been more intense early in our solar system's history. Scientists think that all of this may have caused Mars to gradually transform from what may have been a very nice place to live into the dry, dusty world we know today. And MAVEN will study this process and tell us how it really works.
I want to just play one more piece of this because this is what we studied today. So from about here, this was the process that we tried to work on.
Generates a giant magnetic field that is carried by the solar wind. As the magnetic field sweeps past the planet, some ions will get carried away. Other ions.
Okay, so of all of those scientific processes that we have seen in these videos, we just looked at that one little one because they're so complicated and intertwined. Trying to demonstrate them is very, very difficult. But what we have tried to do is just show that it's a dynamic system where there's a lot of things changing all the time, and how the interplay between all of these is really important. So Maggie, does that help to clear up a little bit of what you were wondering about earlier? Yeah, good. So depending on your own style, you know, you might like to show these videos beforehand so the students have an idea of what it is that they're doing. We were trying to make it more of an inquiry-based process where you would have a guided discussion and then ultimately lead up to this idea of sharing this video to say the actual full story of what it is that we saw, and then maybe give them the opportunity to go back and play again afterwards, but that you can put them all together. So the IMF in the solar wind is the same as the cow magnet. Yes, exactly. So that's why I was using CME and solar wind interchangeably. It doesn't really matter. Basically, it's a source of external magnetic field that's passing over the planet. So whether it's a coronal mass ejection or whether it's just the solar wind, it will have a very similar effect. And the ions that are loose in the atmosphere will just get launched onto it in these Lorentz spirals and get pulled away. Let me just see if there was other. Okay, so does anybody have any other questions? It's a lot to take in, so I would encourage you to go back and to go through the PowerPoint presentation or the PDF presentation, read through these handouts. There's a lot of information in the teacher handout that will help with some context and with some background, and to not necessarily get bogged down in the detail. Like it's still such an open question. We don't know what the answers are, and so trying to, that sometimes the frustrating piece is that when you have students who want to know why and the answer I don't know doesn't always sit well with them. But that would be what I would encourage you to do. You want to make the kids squirm like we made you squirm today. That's fair enough. So does anybody else have any questions? I just need to plug my laptop.
I have a question whether, now that we've done all of this, whether anybody has an idea about how you could use it to demonstrate Earth's atmosphere. Since that's a question that came up before. So I wondered if any of the teachers had thought of something in all this process.
Well, I was thinking, and Claire, you might be able to help me. Would it be fair to say that, you know how we use the DVD disc to be the spacers for Mars? Mm-hmm. For Earth, if you use something thicker, then it would be harder for them to get the iron fillings, because Earth has a thicker atmosphere, has a stronger magnetic field. And so that spacer, that thicker, maybe a textbook, well, I think if you were an analogy for that,
if you were being technically correct, what you would want to do is put a much stronger magnet in there. But since the likelihood of being able to do that is not really possible, then you can kind of switch the perspective of the model and just raise the location or the interaction region of your magnet to much further up. So you would end up having a far less impact on the atmosphere as you try and sweep it away. So that might be a good possibility. Using a bunch of magnets actually doesn't necessarily have much of an effect. We tried to do that with smaller magnets, with just the standard ones that you can buy in in a hardware store, and it actually wasn't nearly strong enough still. So that was sort of surprising. I was kind of surprised at that too. So I mean, if you did have 16 of them, you could certainly try it and see. I would encourage you to explore. I haven't done it, but maybe it's worth entertaining. What about you, Vic? Did that help to answer your ionosphere question a little bit? Yeah? Okay, good. Anybody else have any questions? You can feel free to, have some discussion about this on the Wigio afterwards if you have questions. It's a lot of information, and if you're still hungry for more info, I would encourage you to tune in to the MOI event on Sunday, and the Zoom number is in the chat window, and we can post it to Wigio also. And I would also encourage you to go to the MAVEN website. Let me go back to this here. If I go to the MAVEN website, so this was the website that we went to earlier on to find the education materials. And from this website, if you go to multimedia, And then videos. Well, first of all, there's these 3 very helpful handouts right here. These are just information flyers that you can download and have a read. And if you go to videos, there's an entire archive of everything that you ever needed to know about MAVEN on here. So go for it, have a look through some of them. If you click on them, they take you to YouTube. So here's these 3 that we just watched, the 3 loss mechanisms. And if you click on one of these, it takes you to the YouTube site. And from YouTube, you can go to right here, NASA MAVEN mission. And this has all of the videos that have been produced by the mission that you can just watch one after another. So there's some great ones like this Targeting Mars here. This one is about the orbit insertion and why we need orbit insertion at all. That's well worth a watch. And then down here there is LeVar Burton shares MAVEN stories about NASA at MAVEN. So that's always worth a watch. And then this one here, MAVEN prepared for trip to Mars. There's a few NPR style videos that help with a lot of the background and the context that will be really helpful for just general understanding of what's going on. So I encourage you to go and have a look through those at your own time, your own leisure. And if you find any that are particularly interesting or have a lot of have some points in them that help you to put things together, share them with the rest of the group. Does anybody have any questions or concerns or comments or ideas on how they might use it in their classroom?
Well, this week I am actually covering MAVEN in my classroom, and we started off with the solar pizza activity, and then had the kids come in and do the Earth Mars card sort, and then they actually built a model of the MAVEN spacecraft with cardboard boxes, and I had to go and beg McDonald's for those hamburger boxes for the body. And the kids really enjoyed it. And then we did the spacecraft 3D. Remember I showed that in Colorado? They loved it because then they could actually see it in 3D to help them design the model. But I am planning on using this activity tomorrow with my students.
Oh, great.
Yeah, I ordered the materials several weeks ago, and I still have not received them. So I'm thankful that Andy had mailed that, because now I have something to demo with the kids tomorrow. So I'm definitely going to be sharing that with the kids tomorrow and showing a couple of those videos about the atmospheric loss and what scientists, and I've shared with them about the Sunday, the Mars orbital insertion, and they're all excited, and they're going to see if they're going to watch at 8:30. Now, my understanding is that a live broadcast showing the actual MAVEN going to Mars orbit, correct?
Well, so there won't be a video. There's no video cameras out there. It will be the data that the scientists are collecting. It's called Doppler data. And it will be an explanation of what you see, and then the interpretation of the data, and then there will probably be video. The spacecraft is being controlled out of Lockheed Martin. So they have filmers at Lockheed Martin, so they'll be filming the people who are doing the commanding, and they'll be filming the moment of acknowledgement that, okay, it's been successful and so on. So I'd imagine that's what it will be. So there is no video. It won't be a picture of this. It will just be the interpolated data.
I see. I thought there was a camera on the front of me. No.
Right, not. And that actually brings up a really good question. It's a bit like if a satellite launches itself into an orbit around a planet and nobody's there to see it, did it really happen? So how do you actually interpret what happened, and how do you know that it actually happened, and how do you put the pieces together to know what is, that what you're interpreting is in fact the case? So that's part of the excitement. That's actually going to be one of our presentations here on Sunday, we hope. So that might be beneficial to them too.
Okay.
So I'm doing several MAVEN activities tomorrow with the high school astronomy classes. There's 2 of them. And then on Friday, I'm heading out to North Dakota to the Dakota Nights, and they're having solar observing during the day with a whole bunch of activities. So I'm doing MAVEN activities at that. And then I'm doing a presentation in their, they have a theater that they're doing different presentations in, and they want me to do one there too.
Great. That sounds perfect. Okay, I think that's everything from my perspective, and we're at time. Andy, do you want to do any final wrap-ups?
I would just like to thank everybody for their participation, and thanks to Claire for her great presentation skills and being able to share with us all of her good knowledge. And I'm always blown away at how organized she is and knows exactly where to find things and show things. And thank you to Sally and Maggie and Lynn for working together to help demonstrate this for us and show us how it looks. And thanks to all of you for coming tonight and participating. If you didn't order materials and you would like a set, please make sure that you let me know. I'm happy to get you a set for yourself so that you can go back. This is being recorded, so you can go back and watch it anytime, including on good tips for how to put the model together. Yeah, so thank you. So anyway, I would really, I know I'm going to just be selfish and I'm going to use the word I would really like to see what people do with this on the Widgio, because I love seeing the work that you guys do. So, you know, Molly, definitely let us know how it goes in your class this week, and the rest of you, if you use this activity, please post how it turns out for you. Maggie, what did you want to do with 16 of the magnets? What were you meaning by that? Well, she can unmute herself or not, but anyhow, maybe you can let us know.
I think her plan was to try and emulate Earth's much stronger.
Oh, there you go. Okay, that's what it was. As I was looking at the chat, I don't remember that part. So, okay, great. All right. Well, our next meeting is, I believe, October 21st. A solid inner core. Okay, I see. That makes sense to me now. October 21st is our next meeting. Same back time, same back channel. Dawn, do you want to say just a little bit about who will be presenting then? Do you want to talk about what the presentation is going to be about? She's still on.
We have a really yeah, I'm here.
Oh, good. Okay, great. I couldn't scroll through fast enough. Go ahead.
We have a really exciting presentation lined up. It's a presentation about the social impacts of a large solar storm if it hit Earth directly, and what could possibly happen, like a Carrington event storm, but in today's society with the technology that we have. So it should be really interesting. I've heard the talk before. The speaker gave a presentation at APL, and it was really eye-opening. So I wanted to share that with everybody, and he's agreed to come to our meeting and do the presentation. So I hope you all can make it.
Great.
Thanks, Dawn, so much. Yeah, and when she told us about this presentation, we thought it would be really, really fascinating for the rest of you. So we hope that you'll all join us next month. So, and thanks to Dawn for helping to arrange that. All right, go ahead. Who is talking?
Lynn, and it's the 21st, which is 2 days before the next partial solar eclipse.
Excellent. So we can talk about all sorts of good things that we can be doing with our students and with each other, yeah?
Yeah, I'm already have some things planned. I'm going before the school board in another 2 weeks to talk to them to make sure that all the staff knows how important it is, because it starts at 2:58 our time. Kids are just getting out of school. Don't go home. Don't look at it. Make sure that the teachers all have the materials and what to teach and all of that kind of good stuff. The TV crew is going to come and film us showing all this stuff to the kids. Already got a whole bunch of stuff planned. It's going to be a circus.
In a third alignment of the stars, then the following week is Solar Week, the fall solar week. So all those questions that your students have from the eclipse and that you have after listening to the presentation next month, you can write down, and then you can ask the panel of solar scientists that will be at your disposal for Solar Week. And we can, the idea is that you get your students to ask questions online to solar scientists from across the country, and they answer them in a forum kind of environment. So stars are aligning, or at least the one star is aligned.
Well, thank you, everyone. It's been a lot of fun. I'm glad you enjoyed the activity. And yes, come with your ideas. And Solar Week is it that same week, Claire? Say that again, or is it sooner? I know it's
August 20th, or sorry, October 27th, 31st.
Okay, wonderful. So we'll be able to meet right before that then, and can get everybody signed up. Super. All right. Well, thanks a lot, everyone. Post your stuff on Widget.